Adrian, 50 kilograms, and Bo, 90 kilograms, are playing on a 100 kilogram rigid plank resting on the supports seen in figure 12.33, that's right here. If Adrian stands on the left end, can Bo walk all the way to the right end without the plank tipping over? If not, how far can he get past the support on the right? So now I will start by addressing some givens. So, given, we know the mass of Adrian, denote that as M subscript A, is 50 kilograms. We know the mass of Bo, M subscript B, which is equal to 90 kilograms. We also know the mass of the plank, M subscript P, is equal to 100 kilograms, as well as the distances. So it's denoted that the distance from Adrian to the first plank is 2 meters. The distance in between the two supports, just call that 2, is equal to 3, as well as the distance from the very end, dB, be 4 meters. Don't forget the units. Okay, so moving along. Now there's a few equations that we'll need. So first is torque, which is equal to force times radius, as well as torque counterclockwise is equal to torque clockwise. Now, since the equation is asking how far can Bo be from the right, we know that the right support will need to be at when the force is 0. So we'll use that for our pivot point. We also need to note that the plank, radius of the plank, is equal to 4.5 meters. However, we know that the right plank is at 5 meters. Therefore, we know the radius from the right support is 0.5 away. So that would be handy dandy. So now we'll get started drawing some relevant diagrams. So right here. So right here we have Adrian, 50 kilograms, got the distance 2 meters, our support, which is exerting a normal force in 1, distance 3 meters. We have our next support, denote that is in subscript 2, as well as our main man Bo, I'm sorry, 90 kilograms. This is also times G of gravity. And we also can't forget about the plank, which is, we said, about 0.5 away, roughly right here. So we have 100 kilograms times G. Now, a useful thing to know is we all have, all of these that are exhibiting around this torque here, all use gravity, which is the mg here. So we can exclude that when we write our torque of counterclockwise is equal to torque of clockwise. And we're using this as the pivot point, therefore this force will be equal to 0. So the force going clockwise, which is pulling it this way, we're going to get 50 kilograms, and this is torque net. Oh no, I'm sorry. This is torque counterclockwise, which is equal to torque clockwise. 50 kilograms times the 5 meters, because the distance from here is 3 plus 2, so 5 meters away, plus 100 kilograms times 0.5 meters is equal to 90 kilograms times x. Now, the net torque is going to be equal to 90 kilograms times x minus 100 kilograms times 0.5 meters minus 50 kilograms times 5 meters, which is equal to 0. So all I did here is just subtract this over there to get the net torque right here. So after this, it's easily solvable. Right here, this 100 kilograms times 0.5, that's 50. So we're going to get 50, as well as this 50 times 5, that's 250. So in this equation here, you're going to get 250 plus 50 divided by 90 is equal to x. Therefore, x is equal to 10 over 3 meters, which is also equivalent to 3.3 meters away from the right support. 3 meters away from the right support to the right. And so that right there is how we took the forces. And remember, we could draw the equation. Since all of these have gravity in them, we could just take those out, as well as we were able to solve this system here in order to solve for this x variable that we have going on. And so we use that by substituting into the equations we have. And so with doing these, we use these as well as derive this torque of the net force here, which allowed us to solve this problem to get this 3.3 meters away, which is the distance that he could walk before, or yeah, that's how far he could go without the plank tipping over. Past that, it would tip over. Thank you.